The ratios that are hybrid crosses do differ slightly from this 9331 ratio. This is due to linkage. The genes are located on the same chromosome, as you can see here and here. And the genes that are located on the same chromosome. So sex linkage is the 23rd pair. So this is the X and Y chromosome. From the maternal and paternal genes, and then just so sex linkage is the one on the 23rd chromosomes, which is the mum and the dad, and then autosomal is all the others. This is all the others, so anything else that's not related to sex linkage inherited by the mother or the father. So this is anything else. This is just like, doesn't even have the X and the Y, it's just any chromosomes. And so autosomal is all of them, and then sex linkage is the only ones that are due to the parents. On the autosomal linkage, the linked genes are inherited as one unit. There's no independent assortment during meiosis, unless alleles are separated by the chiasmata. The linked genes do not tend to undergo random shuffling of alleles on autosomal linkage. That's why autosomal linkage is more likely to get this than the sex-linked ones are. The closer the loci of the gene on the chromosome, the less likely they'll be separated during crossing over, and fewer recombinant offspring are produced. So, what is a recombinant offspring? Recombinant offspring. So what is a recombinant offspring? This is a different allele combination to both parents. So when you have, at the crossing over stage, this is in prophase 1 of meiosis, so prophase 1. Remember, this is just sex linkage. This isn't autosomal linkage. This is in sex linkage. During crossing over in prophase 1, there's non-sister chromatids of the homologous pairs that break and reform. So non-sister chromatids on the homologous pair may break and then reform again. As they break at the same point, any gene located below the point of break will be exchanged as a result of the recombination, forming a new gene combination. So as you can see here, as they break here, any gene located below the point of break, which is if they break here, any gene located here will be exchanged as a result of the recombination, and this can form new gene combinations, meaning that it's a recombinant offspring, because it's not the same gene combination as the parent. Therefore, the recombination frequency, which I'll show you in a second, is the measure of an amount of crossing over that has happened in meiosis. So obviously the extent of the crossing over can be altered. So how do you work out the recombination frequency? The recombination frequency is, if I put RF, the recombination frequency, to work that out, so that's the amount of crossing over that's happened in meiosis, is the number of offspring, number of recombinant offspring divided by the total number of offspring. So that's general. So you always have what you're trying to find out at the top, and then you have all the numbers total together at the bottom. So the number to find out how much crossing over there was, number of recombinant offspring that there were divided by the total number of offspring. So when you have your data, what does it mean? How do you analyse it? So a recombination frequency of 50% means there's no linkage, and the genes are separate chromosomes. So the genes that you've had, it's a very small diagram, these are the genes, these are just separate and there's no linkage involved in the chromosomes. However, if the recombination frequency is less than 50, so less than 50, this means there is gene linkage. So the smaller you are, yes, there is gene linkage. And the random process of independent assortment has been hindered. So the genes are together and there's no independent assortment, which has caused different changes in the genetics.